In number 3, we've got a little bit different setup going on in that we don't have a sum of squares, but a difference of squares that we're working on. We also have that square root showing up in the bottom as well. That just makes our problem even worse. We don't like having sums and differences in the bottom of fractions a lot of time because you can't split the bottom of fraction the way you can the top. Having the square root just makes that even more of a problem because you also can't split square roots over addition or subtraction. So if we remember, I'm going to scroll up here. Our little tips at the top, if we have difference of squares, we're either going to use a sine or a secant. Since we had a 9 minus x squared, we definitely want the sine. We're going for this that I have right here, where if we can get down to a 1 minus sine squared, we can replace it with cosine squared. So we're going to use a sine in this problem. More specifically, we're going to say that if we want to factor and end up with 1 minus sine squared theta, we need w to be 3 sine theta, so that when we square it, we get that 9 to factor out. This means that the dw is going to be 3 cosine theta d theta. So back up here, we have a 3 sine theta over the square root of 9 minus 9 sine squared theta. Don't forget that you have to square the whole thing, so the 3 does in fact become a 9. And then we have a 3 cosine theta d theta. Okay, so again, as much or as little of this as you need to show. I can factor out a 9. I can say that 1 minus sine squared is cosine squared. And that means that in my next step, I'm going to have a 3 sine theta over the square root of 9 cosine squared, which is going to be a 3 cosine theta. Okay, and there's a little funniness. When you take the square root of a perfect square, you actually get an absolute value out of that. But the domain restrictions that we would get here allow us to kind of ignore that. So I'm letting you off the hook on that a little bit, but there is some stuff to think about there. Okay, so the 3 cosine thetas disappear altogether, and we're left with 3 times the integral of sine theta d theta. The antiderivative of sine is going to be cosine, but when we take the derivative of cosine, we actually get minus sine, so we need an extra negative here, plus c. And then we're in pretty good shape. We've actually gotten to take the integral, but we need to get back to w's, and there's going to be a little bit of work to do here. We know that sine theta is equal to w over 3. Which means if we draw our triangle, theta, we want opposite over hypotenuse to be w over 3. And then the Pythagorean theorem says that this is going to be equal to hypotenuse squared minus the other leg squared. So we can come to this answer that we got and say, okay, but cosine theta is actually the same as a square root, oops, what am I writing? There we go. It was 3 squared, which is 9, so it's going to be a square root of 9 minus w squared over 3. And if we cross out those 3, that means we're getting negative square root 9 minus w squared plus c. Okay, thanks for watching.